Welcome, students of geometry, to lesson 12.5. Today we're talking about volume of pyramids and cones. And so let's start by looking at the theorems, or the volume formulas themselves. So the volume theorems, the volume formulas for a pyramid, put that on the left side here, that's theorem 12.9 in our books, and the cone is going to be theorem 1210. And the volume formula for a pyramid, it is, I'm going to let the tension rise here for a moment. And I'm going to do a little demonstration here to show you why this is what it is. So here is a prism, rectangular prism. It actually happens to be a cube, but we'll refer to it less specifically as a rectangular prism right now. And here is a pyramid. It has the same height and the same base. They're both squares. Ooh, there we go. They're both squares that have the same area right there, and the height is the same. I can fit this inside there, and it's going to have that same height right there. Boom, right there. So what is this compared to this? We know that the volume of any prism is base times height, the area of the base times the height. That's how much water I could put in here. And how about this? What is this compared to this? They have the same base, they have the same height. Let's make the comparison. So I've got a cup of water right here, and I'm going to fill up this pyramid with that water and hope I don't spill it on my laptop, because that would be pretty awful. Alright, so there's one fill. Now I'm going to pour this into here. That was one. So I still got a little ways to go, clearly. Let's fill it up again. So fill up number 2. There we go. Got it filled up twice there. There's a second one. And still got a little bit to go here. I'm going to fill it up 3 times. I'm not sure if it'll fit the whole time. Actually, I'm quite sure exactly what's going to happen because I've done this before. But see what we got there, and would you look at that? It filled it up. I did leave just a tiny bit with the pyramid. I didn't fill it up quite all the way, so there's just a tiny bit left over here, just because I didn't want to spill. But there it is. You can see that 3 pyramids with the same base and height filled up the prism that goes along with it. So what does that mean in terms of the area formula? It means this. That wasn't a proof of why this works. That was just a demonstration, a singular example of why that worked. But the pyramid pyramid volume is 1/3 of what the prism volume would be. So it's 1/3 base times height. And over here, the cone ends up being the same exact thing. So 1/3 base times height, but this is going to equal the base being a circle and a cone would be 1/3 pi r squared times the height. That's the way we'll probably think about it more with cones, or the way we should think about it more. And so we have B being the area of the base, still just like we've had all along, H being the height, R being the radius. So we're going to use this for cones, we're going to use this for pyramids. So right now I want you to draw a hexagon, but we're going to be looking at it on a bit of an angle. So here's a hexagon, and if you have a pencil, you can do this in a solid line format, but if not, you should make these hidden lines back here go straight up from the center. And we're actually going to make this an oblique one, so I'm going to go, here's the center, but I'm actually going to go to the left a little bit on this one. So an oblique pyramid, this actually works, this formula works with oblique pyramids or right pyramids or regular pyramids. It doesn't have to be straight up and down with volume. So we're going to do one where it's on a bit of a slant. It's an oblique pyramid. Looks like I'll just be able to see that one too. So going to make that one dark, and then this one's going to be hidden back here. I wouldn't be able to see that one. And then I'll erase little bits here, erase the bits there. Okay, so I've got my oblique pyramid. I'm going to tell you that the straight up and down height, the perpendicular height here is going to be 5 centimeters. And I'm going to tell you that the side length here is 2 centimeters. And you can make some markings on this picture to denote that all these sides are the same. We'll make tick marks. So we've got congruent edges there. This is then a regular hexagon. So H representing, let's make a note of that here. H is the perpendicular height. Perpendicular being the vital word there. It's not the height on a slant, it's not slant height, it's not the height of this particular part from here up to here, but it's this perpendicular height. So that's what we got going on both places here. The other things we know what those stood for from before. H, we knew that was height from before, but just know that it's perpendicular height. You can have stuff on a slant a little bit like this with volume for pyramids and cones. So from there, what do we know? We know the base is a regular hexagon. And because that's the case, let's draw a hexagon over here. So if we were looking at it straight on, base being a regular hexagon, we could split this up into 6 triangles. And the nice shortcut with hexagons is that we know they're all equilateral triangles. And so we have 6 equilateral triangles. And therefore, we can take what we know. We know that these would all be the same here, here, and here. This is 2 centimeters. We found the area of one particular triangle there multiplied by 6. Then we'd have the area of that whole hexagon, the area of the whole capital B, base, the area of the base. And so this volume is going to equal 1/3 times B times H. Let's fill in what we know, figure out what we don't. So we know that the area of the base is going to be, there's 6 of those equilateral triangles. The shortcut formula for equilateral triangles was s squared times radical 3, all divided by 4. So our side squared is going to be 2 squared. We have that times radical 3, all divided by 4. And I guess I didn't really need to put that in brackets. Brackets, though, are just special parentheses. So I have 6 equilateral triangles here. Let's take this and boom, put that over here. That's where this whole thing comes from. And we have that now times the height. The height is 5. Height is the perpendicular, or straight up and down parts. From there, we can type stuff into a calculator. I do notice, though, that 2 squared, that would become 4. So why don't I do that first? I've got 2 squared equals 4. And so I'd have the 4's and the 4's could cancel here and here. I'd have 1/3 of 6, which would be 2. So this could become 2 times radical 3, and we still have that times 5. So an exact answer would be this, 10 radical 3, and that would be in terms of centimeters. This is volume now, so centimeters cubed. This would be an acceptable answer. An approximate answer that would be acceptable if we round this to 1 decimal place. It all depends on what the directions say. I'm going to tell you, let's go to 1 decimal place right now. You type this into a calculator, you're going to get 17.3 centimeters cubed. And that's it. That's what we have to do for the volume of a pyramid like that. So I tried to do a slightly more difficult one here than some you might see. Some might just be a triangular base or a square base. Those are the easiest because you just do side times side. This one happened to be a hexagon, though. Sometimes it'll be harder. You'll have that apothem method that you'll have to use, where you have to find an area of a pentagon or a heptagon. or an octagon or nonagon or whatever gon, based on using some trig, finding the area of one triangle, multiplying it by the number of triangles. But let's check out example 2 now. A second example, draw a cone for this one. And this won't be a to scale drawing necessarily, but we've got our circle as a base right there, center points in our different color. Let's include these things in here. This is going to be 10.2 meters, and the radius is 6.7 meters. And that's going to be perpendicular right there. We're going to say this is a right cone, so it's straight up and down, not oblique, not on a slant. The volume formula, we're going to figure out the volume here. The volume formula for a cone, remember, is the same thing as for a pyramid, but your base is a circle, so you can replace the capital B with pi r squared. So we have 1/3 pi r squared times the height. Plug in the numbers and go from there. So your radius, that's 6.7, you have 6.7 squared, times the height is 10.2, and at that point, you could put that into a calculator, and you'd get this. I'm actually going to bring the calculator up here just to double check my work. So I've got 6.7, and I'm going to take that. That is not working. I didn't click it down there yet. 6.7 times 6.7. That's 6.7 squared times 10.2. We have that times, now 1/3. I'm going to write that in parentheses here because I want to do 1 divided by 3 first and then multiply. Not 30. There we go. 3 and parentheses. There it is. And so that's 1/3, 0.3 repeating. Multiply all that together. That gives me this 152.626. So I have 152.626. This is an exact answer, and that would be in terms of pi, because I still have a pi right there. And so that would be in meters cubed. That's an exact answer. I didn't round the decimal off at all. That's exactly what it was. And approximate answer, we're going to take that value, multiply it times pi. So this times pi gives me a really, really good approximate answer here, 479. Let's say I went to 2 decimal places on this one. I'd have 479.49 meters cubed. So you have an exact answer and an approximate answer once again. You should know how to get both, read the directions to see which one they want. A quick little note here, and then we'll do a third example. So if you were doing oblique cones, for oblique cones, we'll take a look at this in just a moment. You should check this example out. You should check out example 2. This is a B, not 26, a 2B. So example 2B on page 753. You're still going to use perpendicular height. And so here is example 2B. They have an oblique circular cone. Here's one like the one we just did, but here's one that's oblique, but you're still using that perpendicular height. So it's really the same exact formula, nothing's different at all. Just make sure you're using the straight up and down height, not the height given on a slant, if it is given on a slant. If they gave you the slant height and the radius, we could figure out the perpendicular height based on the Pythagorean theorem. You would just have to do h squared for height plus the radius squared, which would be 12.4 squared, would equal the slant height if they gave that value, or that length to you. I'm sorry. So from there, you know all that stuff. Let's see. Got for oblique cones, we're checking out that page. And so now example 3, let's check this out. This one we'll make a little wider. Doesn't necessarily mean that it's going to be drawn to scale, but just make a wider cone, just so you know that cones don't always have to be that same sort of shape. Sometimes you could have this wide one. Maybe this looks like kind of like one of those traditional Chinese hats that I have seen some people wear to block out the sun, or to keep the sun off their we're going to say that that right there is 15 feet. And this one, the radius, I'm going to say is an unknown quantity. I'm going to call it x feet. I don't know the radius yet. And I'm going to tell you that this is given that the volume is 2262. It's 2,262 feet cubed. So this is one of those cases where we need to take the formula, write it out in general again. This is for a cone, so take the formula in general. We have this, plug in what we know, and solve for what we don't. We are solving for x because x represents a radius, that is the unknown quantity. So we're going to be solving for the radius here. Plug in 2262. I know that's my volume. My radius, calling it x. So I have x squared times the height. I know that, the perpendicular height, the straight up and down height. Let me put a box there just so you know that that's perpendicular. Straight up and down, we've got 15 feet right there. So this one worked out nice. 1/3 of 15, this is all multiplication, so the order doesn't matter. I can do 1/3 of 15 as 5, and so I've got 2262 would equal 5 pi times x squared. From there, let's use our different color to show the steps. We're going to divide by 5 pi to get x squared by itself. That'll go away right there. I'll have 2262 over 5 pi equals x squared. From there, I can take the square root of both sides. So I'm just going to take this and put that into a calculator. When I do that, I've done this work beforehand, I get approximately 12. It's really, really close to 12. And so 12 feet is going to be my final answer there. 12 feet for the radius represented by x up here. And so that will actually almost do it for us. We've got one more thing that I want to talk about here. So let's bring up the book a second for that. Some cool real-life applications of this. Nautical prism. Before electricity, nautical prisms were placed in the decks of sailing ships. By placing the hexagonal face flush with the deck, the prisms would draw light to the lower regions of the deck. So pretty cool that even if the bottom didn't have windows, you could use these nautical prisms. It would spread the light out from the top floor, and as long as you had something like that, you would have light in some of the bottom floors, some of the floors that you couldn't have windows in because it would be right against the water, and there might be chances of leaking and whatnot. So before modern day times, that would have been a pretty scary or dangerous thing to do, to have windows right next to the water. Now we have plenty of stuff that makes it easier to do that, plenty of sealants and whatnot that makes it a fine thing to do that. But before then, yeah, a little difficult to get light down to the lower level. So you can use that idea to figure out the volume of this nautical prism. How much glass would you need for a nautical prism? Something like that. You can also think about how much, this is oil being poured into a funnel, like how much oil can the funnel hold. If it's flowing through the funnel at a certain rate, how fast can you pour, things of that nature. Pretty cool stuff. Engineers would use things like that all the time to make sure they got enough. So you're going to see some other real life connections here. How much food can you feed your cat with this thing? Is this for a cat? It's just a pet feeder, I guess, and whatnot. As you go through here, Mount St. Helens, the volume of that, really cool place if you've never been there. Glad I wasn't there when it blew up in 1980, though. I wasn't even born yet. You weren't either, probably. Yep, that'll do it for us here. I am all set with that. It should be a really good, solid basis to start your classwork there. Let me know in class if you had any questions, and hey, have a good day. I'll see you guys later.